Susskind has been the Felix Bloch Professor of Theoretical Physics at Stanford University for 28 years.
Susskind visited New York this week to introduce his first popular science book, The Cosmic Landscape, String Theory and the Illusion of Intelligent Design. In the book, Susskind aims to debunk what he calls the narrow 20th century view of a unique universe.
In a lecture at the New York Academy of Sciences, he described a megaverse that is the result of a vast range of mathematical possibilities. Science in the City spoke with Susskind before his talk. You've been at Stanford for how long now?
Since 1977.
So this is the first time you decided to write a popular book?
It is.
Why now? Why,
That's an interesting question. I always believed that I couldn't write. My teachers had told me, "You're a miserable failure as an English scholar. You can't put a sentence together." And somehow I knew that that was wrong. I knew that that was wrong. I knew that I could write good, clear English prose, but I was always intimidated by it. Until a number of years ago, I was asked to write a couple of magazine articles. I figured, okay, a magazine article, that sounds pretty easy. I'll get somebody to help me if I run into trouble. And I started writing, and I got terribly absorbed in it. And what came out was good. People said, that was really, really good. And that was it. I just realized I really enjoy explaining physics. I enjoy teaching it. And the idea of writing a book for the public just caught my imagination, and I got excited by it, got thoroughly absorbed in it. And I just had a load of fun thinking about how do you explain things, how do you explain difficult things to a general audience. And in doing so, I think I learned a lot myself, figuring out how do you explain something that I know how to explain to a physicist, but I don't know how to explain without equations. Let me think about it. And in doing so, I learned much more than I ever expected.
I read somewhere that you were going to originally be a plumber.
Yes, this is true.
See what it's about. Well, you're originally from New York. You're from South Bronx.
South Bronx.
And now we've lost you to the West Coast a while ago, I guess.
Yeah, I still have, these feelings of, is it nostalgia or familiarity with the city? When I find myself in the city, all of a sudden I'm a New Yorker again.
So what happened? Plumbing didn't work out for you, or?
My father was a plumber,
uh-huh.
And I didn't know anything about science. I didn't know. I was a 19-year-old kid. I had no idea that you could be a scientist. I got married. I had a child. My father expected me to come into business with him, be a plumber. Incidentally, being a plumber meant, among other things, cleaning sewers. It was a filthy, miserable business. I had done it since I was 15 years old. I was a member of the plumbers union. I was a journeyman plumber. I really knew how to, and we worked in these dirty tenement buildings, and I hated it. I really hated it. I escaped from it by, first of all, going to college, but the reason I went to college was to become an engineer. The idea was to become a heating engineer so that my father and I could work on boilers and big furnaces and things. That was the whole idea. Of course, the first thing I noticed was I really couldn't stand engineering, and what I loved was physics and mathematics. And I ran into a situation where an engineering professor, a fellow named Harold Rothbart, who became a friend of mine, told me during an engineering class, "Susskind, I'm going to fail you. You're a failure at this subject. You can't do engineering." And I said, "What am I? Oh my God, I have a child, I have a kid, I have to get to my father, and we got to do plumbing." And he said, "Nope, I'm going to fail you unless you do one thing." And I said, "What?" He said, "Drop out of engineering." And I said, "My God, what am I going to do?" And so I went around to the various science departments, and eventually I met Professor Sudak, who's sitting downstairs right now.
Right.
He's chomping a big cigar. He's a regular guy. He knows about physics, and I liked physics and when I took it. And he said, "You can be a physicist." And so I said, "Okay, I'll try being a physicist." And of course, within 6 months, I was hooked. Really hooked. I mean, really hooked. I knew I wanted to be a physicist. I very quickly started asking quick questions. Then, of course, came the problem of telling my father that I'm not going to be an engineer. That was a tough point in my life.
But I assume he took it, and I'm sure he would be proud of you. No?
Yes and no. I had to go to my father's house to tell him that. So I packed my wife, and I little baby in a car. We went over to my father's house. My father, understand, was a South Bronx plumber. He was a tough guy, curse a blue streak. And I said to him, very scared, twice as big as him. He was a little wiry guy, but he scared me. And I said, Papa, I ain't going to be a plumber. He said, well, what the bleep do you mean you're not going to be? What are you going to be, a ballet dancer? I said, no, I'm going to be a scientist. He said, a physicist. So what's that? And I said, a scientist, the same kind of scientist as Einstein. Well, that did it. Einstein. Are you good at this? I said, yeah, I'm pretty good at it. And he took his piece of pipe that he was holding, and he pushed me in the chest, and he said, God damn it, you ain't going to be no plumber. You're going to be Einstein. And that was it. From there on, he tried to learn physics. He got all excited about it, and that was it. His son the physicist.
And in the book, you go into string theory a little bit, and you talk about how scientists are looking for elegant answers and beautiful answers. And what is a beautiful equation? What is an elegant equation?
This, of course, elegance is in the eye of the beholder, of course. And at what stage you expect elegance is another question. Old Kepler had looked for very elegant equations or a very elegant mathematical theory of the solar system. And so he thought that the 5 known planets could be put in one-to-one correspondence with the 5 regular polyhedra. This was a harebrained idea, but he made a very, very beautiful mathematical theory of the solar system based on the 5 regular polyhedra and how they nested together. And it was beautiful, it was elegant, it was unique, and it was utter rubbish. It had nothing to do with the real thing. The real truth is that the solar system, the orbits of the planets, the radii of the orbits of the planets, they all depend on the history of the solar system. They depend on all kinds of details. And the numerical values of the radii of the orbits are not in any way very, very special numbers, square root of 2, pi, anything like that. They're a consequence of history. They're a consequence of nuclear physics. All kinds of things went into it. And they're just more or less, I won't say random numbers, they're environmental numbers. Physicists had always hoped that questions like what is the mass of the electron, what is the value of the electric charge, all these kind of questions would have these simple, beautiful answers of the kind that Kepler imagined, that they would be very simple numbers, square roots of 2, or generalizations of that, and that there would be some deep underlying, beautiful, simple mathematical equations that which, when you solve them, would explain all the details of elementary particle physics, the electron, the proton, the neutron, quarks, and all these things, and everything would be absolutely unique. This was the goal. This was the I suppose one would call it the Holy Grail. The opposite idea was that all of these numbers that we experience in physics, all of the properties of the elementary particles, may in a sense be environmental. They may be properties of the history of our universe. They may vary from place to place. They may vary the same way that the orbits of planets from one star to another may vary, and that some of the features of what we usually call the laws of nature may be environmental. And if they are environmental, then certain properties of the laws of nature are going to be determined, not determined, but are going to be contingent on that the laws in our particular vicinity are capable of supporting our own selves. So this is a debate. It's a fierce debate that's going on between physicists. In fact, I would say it's so fierce that it sometimes takes place in the individual heads of individual physicists. Sometimes I argue with myself about it. But the question is, are all of those properties things which are going to be uniquely determined by a beautiful mathematical set of equations, or are they going to be just environmental properties of our little local patch of the universe? And this, as I said, this is something that physicists feel very passionate about one way or another, and it has led to a fierce, it's hard to call it a battle.
I attended a panel at the Museum of Natural History over here. Andre Linde was there.
Oh, I see. My colleague.
Your colleague.
My friend.
We read about very well in the book. And Michio Kaku was there. And everyone was going back and forth about this. And that's what's kind of leading me into my next question, because Linde at that point brought up the anthropic principle. So I was hoping you could riff on that a bit. And I don't think it's something that people are very well familiarized with, at least the popular audience.
The general question is, why are the laws of physics what they are? And one possible answer, as I said, is because they couldn't be anything else. The mathematics requires them to be a certain thing. But another answer is, now this sounds really goony. This sounds so screwy that physicists have generally, for basically all of the past century, rejected it. The idea is the laws of nature are what they are, just so that physicists can be here to observe the universe and ask the question, what are the laws of nature? Now, that sounds silly. That sounds absurdly silly. But what we really mean by it is something different. Not different, that's part of it, but what we really mean by it is the following. We know the universe is extremely big. Now, when I say it's extremely big, I don't mean big like we used to think it was 20, 30 years ago. We used to think it was something like 10 billion light years in size. We now suspect that it's vastly, vastly bigger than that. The success of various inflationary theories have taught us, if they've taught us anything, that the universe is vastly, vastly bigger than the part that we can see through telescopes of any conceivable kind. It's extremely big. Given that, all we know about the universe is a tiny, tiny little corner of it. A corner which is so small that we no longer have any reason to believe that it's representative of the whole thing. So the question then arises, is the universe extremely big but all of a piece, meaning to say all the same everywhere, a sort of uniform monocolored blanket, or is it a patchwork quilt, a crazy quilt of different kinds of environments with different properties, with different laws of physics and so forth? And there's much that we've learned over the last few years that are tending toward pushing us in the direction of a patchwork quilt. Different properties in different places. If that's true, then some things about the laws of nature, some certain things are going to be determined by nothing more than whether we can live in a certain place or not. Certain regions will just be forbidden. Forces won't be reasonable, chemistry won't exist, chemistry doesn't exist, biology doesn't exist in those places. And so some things will be determined by just the fact that we're here. And that's what most physicists who think about anthropic principle really mean. The universe is very big and very diverse, and we live where we can live, and that's the end of the story.
Alright, so just by sheer force of the vastness of the numbers.
Sheer vastness of the numbers. It's very much like the same question, why do we live on a planet which happens to be just so that liquid water can exist? You have to be in a very narrow range of temperature. Some physicists, had they not known better, might have said, let's find an equation which tells us that the temperature of the Earth, figure out an equation which will tell us what the temperature of the Earth is, and then, by luck, it'll be that the temperature is such that liquid water can exist. Now, we know that that's not right. We know that there's just a huge number of planets out there. Some of them are too far from their stars to have liquid water. Some of them are close to the stars, and so they just evaporate the water. A very small number of them happen to be at the right distance so that liquid water can exist. That's where life can exist. And so it's no mystery why we happen to live in a place where liquid water exists. It's not the solution of some fancy equation. It's just the fact that we can't live anywhere else. The same may be true of many of the properties of elementary particles. They may be true of many properties of the constants of nature, that they vary from place to place. And if so, then certain features of the laws of nature will be contingent on the fact that we're here to observe them. So it's not a great mystery.
Well, I mean, I guess it could be easily taken out of context
yes.
as well. And
for example, there are people of a religious persuasion who think that the anthropic principle means that the universe was especially designed for our own benefit. I don't subscribe to that. In fact, quite the opposite. I think the universe is a big random place, most of which is not hospitable to us, but some very, very small, tiny fraction of it is livable. So it's quite the opposite from the religious-based idea. On the other hand, both camps would say the universe is the way it is, just so physicists can be here to observe it. So,
got it. The title of the book is The Cosmic Landscape, and I assume that that's basically your construct, the idea of this landscape.
Yes and no. I think I named it.
Okay.
When you name a thing, it often means that you're the person who realized its importance, who realized the context, who realized that there's a thing there to name. But the ideas were being generated by, well, for one person, Andre Linde, but Joseph Polchinski, Raphael Busso, a whole group of people were beginning to get the sense that this enormous diversity existed. And papers on string theory were beginning to go in that direction. And so I think probably more than anyone else, I was the one who sort of focused attention on it and said, hey, look, fellows and girls, is not going the way we thought it was going. There does exist this enormous landscape of solutions, and so calling it the landscape sort of focused attention on it.
But now the landscape, the cosmic landscape that you're talking about in the book, is not necessarily a place.
It is not a place.
That's
right.
A set of possibilities.
Yeah, physicists and chemists use the word landscape to describe the possibilities, not the actual things. They describe, for example, the landscape, biologists use it, the landscape of biological design. This means all the ways that you could rearrange a DNA molecule. How many ways are there of rearranging a DNA molecule and changing the base pairs? 10 to this enormous number, 10 to the billionth, some enormous number. And so the space of all of these possibilities, which represents the space of not only all possible living creatures, but even the ones that wouldn't be viable, all possible life, not actual life, but all possible life, all the possible blueprints for life, that constitutes the landscape of biological designs. The actual biosphere it sort of populates that landscape. So the landscape of cosmology is again the landscape of possibilities, enumeration of all the possible kinds of environments that could exist.
And then the universe is the Megaverse, whatever you want to...
That would be more like the biosphere.
That's the biosphere.
The actual stuff. Yeah,
right.
The actual stuff that materialized. And then one even speaks about populating the landscape, which means all the possible pockets of space that have different properties, each being itself a realization of some point on the landscape of possibilities. And the remarkable discovery, which, as I said, was actually made by people doing a more technical kind of thing than I was doing, was that string theory has this enormous landscape, that the number of possible different designs, the number of ways of rearranging the pieces of it, is so vast that it's like the biological landscape. Just an enormous number of things can exist.
I mean, I guess this leading to the fact that there could be this megaverse with all these pockets of different universes, completely unfathomable to us, the number.
Absolutely. Yeah.
Assuming, let's say, we're assuming that this is way beyond where we can contact them.
Way beyond.
We're not going to be able to get there.
Yeah.
What is the validity of asking these questions?
We have reached a place and a point in science where answering almost any of the questions that we're interested in has become exceedingly difficult. The kind of questions that elementary particle physicists, people who are interested in the quantum mechanics of gravity, all of the deepest questions, connection between relativity and gravity, they all involve a range of parameters which are so distant and so remote that it looks almost hopeless to make direct experiments. We have to rely to more than we would like on theory and circumstantial evidence. But this is not a totally new situation. Let me give you some examples. Darwin had lots of circumstantial evidence, but could he ever go back in time and directly confirm that species were changing, that species were evolving. Of course not. He'd have to go back billions of years in time. So he always had to use circumstantial evidence and deduction and a good deal of theory to substitute for the actual observations that nobody can make and nobody ever will make. The situation is somewhat the same. We have to deduce from what we see, which is a very limited amount, we have to deduce what the rest of the world might look like and how the rest of the world may be. Are there implications of this idea, of these ideas? Yes. Stephen Weinberg was one of the first to ask, is there an interesting implication of these anthropic ideas? And his idea was that the anthropic ideas could explain the smallness of the cosmological constant. It was thought to be zero exactly. Nobody knew why it was zero. All we knew is that it was incredibly small. Weinberg said just maybe the reason it's so small is because we couldn't live in a world where it was a little bit bigger. And so he went back and figured out, again, a circumstantial piece of evidence, a deduction rather than an observation, that if the cosmological constant was very much bigger than this incredibly small number, 10 to the minus 120, that planets, galaxies, stars could not have formed, and therefore we couldn't be here. So he said, just maybe the explanation of this particular number is this anthropic idea that we couldn't be here if it were very different. But then he got even more brilliant, and he said, wait, but if that's the only reason this number is so small, there's no reason why it should be very much smaller than what's needed for our survival. So he predicted that in the next round of experiments, the number would not be zero, that in the 121st decimal place, imagine that, 100 decimal places all zero, he predicted that the astronomers would in the next round discover 121st decimal place. And they did. And they did. So anyone who says that this doesn't have implications is not right. But the implications are far and in between and very, very difficult to confirm. To a large extent, we're reliant on more theory than we would like and less observation. Who knows what the future will bring? There will be other tests. There will be other ways to confirm. There are two conjectures out there. Both of them are very conjectural. One of them is the universe is the same everywhere, and the other is that it's different in different places. Both of them are conjectural. Both of them are very, very difficult to confirm. One of them fits what we know better than the other. And we'll work from there. So I wish I could tell you that here's all you have to do is point your telescope in that direction over there, and you'll see the some other pocket universe. But no, that's not the way it'll be.